Hi, I'm Kevin Dorma. Welcome to part 3 of my series on the waterside dynamics of a once-through steam generator. This section will begin with the waterside response to the light-off of an OTSG. Then, we will look at a sudden decrease in the boiler feed water flow rate. For OTSG light-off, the firing rate is set to the minimum stable value. The boiler feed water flow rate is set to produce the normal steam quality. All of the flow exiting the OTSG is routed through the back pressure control valve to a startup pond. The startup control valve maintains the OTSG at a fixed pressure, 10,000 kPa in this case. We saw in the previous walkthrough that the OTSG begins completely liquid filled and ends about half full of water. What takes place during this transition? I have heard stories about the back-end PSV routinely lifting on startup, and concerns about excessive pipe movement on the startup line. How can we avoid these problems? Water enters the OTSG at 600 kilojoules per kilo, about 150 degrees. At light-off, heat is added uniformly along the tube volume. The outlet enthalpy, or temperature, increases at a steady rate. There is about 10 cubic meters of tube volume that is nearly at the boiling point. Any additional heat will cause uniform expansion along the entire volume of the radiant section. The animation continues and we see a rapid increase in the outlet enthalpy. The 10 cubic meters of water in the radiant section is replaced with wet steam. The sudden emptying of the OTSG is easier to see with the trend of the outlet mass flow rate. The outlet mass flow starts identical to the inlet mass flow and then increases slightly at light-off. This is because the decreased density in the OTSG has caused the outlet mass flow to exceed the inlet mass flow. The outlet temperature increases gradually as a result of the sudden increase in firing rate. The entire back end of the OTSG is at the boiling point at the 15-minute mark. The outlet mass flow increases almost 10 times as the steam fills the radiant section and displaces about 10 tons of water. After another 2 minutes, the outlet mass flow has reduced to near normal values. This requires the startup control valve to act very aggressively, and it probably does not have the capacity to manage this enormous flow rate of flashing water and steam. Light-off displaces a large volume of water. In this case, about 10 cubic meters. Reducing the volume of water that is displaced during light-off will reduce the surge that taxes the capacity of the startup valve. We can reduce the volume of water by targeting a lower enthalpy or water or steam quality that exits the OTSG. Then the OTSG will displace, say, 2 or 3 cubic meters of water rather than 10. We cannot decrease the firing rate anymore, but we can increase the boiler feed water flow rate. This will increase the steady state flow rate of water and steam, but it will decrease the liquid volume that is displaced when the radiant section reaches the boiling point. Let's see how this plays out. By increasing the water flow rate, we see that the water will reach the boiling point further down the OTSG volume. This decreases the volume of water that is ejected when the back end starts to boil. The final enthalpy, or steam quality, is also reduced. The trend for mass flow rate out of the OTSG tells a clearer story. The steady state flow rate out of the OTSG is higher, but the peak is much smaller. The startup control valve will have a much better chance of keeping the pressure on set point. Notice that the OTSG reaches steady state in exactly the same time as compared with light-off at the lower flow rate. The next transition is a sudden decrease in the boiler feed water flow rate. This could be caused by a sudden drop in the feed water supply pressure caused by shutting down one of the high-pressure pumps. The response that we see is a sudden increase in the measured steam quality, but the level in the steam separator drops slowly. How do we explain both observations, and does a sudden water shortage cause a problem? In this example, the OTSG is fired at design rates and the water flow rate is set to yield a steam quality of about 50%. Then we cut the water flow by 30%, which will yield a steam quality of about 90%. The first thing we notice is that the outlet enthalpy is increasing very slowly. This is reminiscent of the slow change in outlet enthalpy that we saw in the light-off example, where there was a sudden increase in the firing rate. The animation has paused at 2 minutes, and we see the effect of the new marching orders that have been given to the fluid in the OTSG tubes. The small kink in the enthalpy indicates where the OTSG has been fully affected by the change in flow rate, just like the kink in the enthalpy that is associated with light-off. The water volume has decreased from 11 cubic meters to about 10. A loss of 1 cubic meter has occurred over 2 minutes. We keep going, and the outlet enthalpy continues to slowly rise for 7 minutes after the sudden drop in boiler feed water flow rate. The OTSG has lost 3 cubic meters of water over 7 minutes. The trend of the actual steam quality, the black line, and the Venturi steam quality, the red line, tells us a conflicting story. The actual steam quality, black, rises slowly because the new marching orders travel slowly through the liquid-filled section. But the extra water that is kicked out shows up as extra and unmeasured mass through the Venturi. This is interpreted as a false high reading from the measured steam quality. The best indication of what is really happening is the level in the steam separator, the blue line. This is provided that the level controller is tuned slowly. The level slowly drops off rather than seeing a sharp change in slope. A sudden drop in the boiler feed water flow rate looks a lot more serious than it really is. In the long term, there will be the inevitable increase in steam quality. But in the short term, the Venturi steam quality reads false and overstates the steam quality. Consider softening pass flow deviation trips or steam quality trips and give the control system the opportunity to do its job and bring the flow rates back to normal. This will avoid spurious OTSG trips and avoid the most hazardous operating mode, light-off. Note that the response for the increase in firing rate is nearly identical to a decrease in boiler feed water flow rate. The waterside behavior to a change in firing rate or flow rate is important when we look at process control, where we change the firing rate or water flow rate to adjust the steam quality. This behavior also comes into play with alarm or interlock settings for pass flow deviation and steam quality. The objective is to ensure that interlocks are only activated when necessary. An unnecessary firing trip results in a potentially hazardous relight. In Part 4, we will look at how the waterside responds to sudden increase and decrease in boiler feed water temperature. I'm Kevin Dorma. Please visit my webpage at www.kevindorma.ca for more information. Bye for now.